Somewhere in Belfast, Northern Ireland, buried nearly 60 feet underground, there is a piece of the Titanic that the ocean never touched. No salt water, no pressure, no decay, no rusticles slowly eating through the steel, just soil. Cold, dark, perfectly preserved soil, wrapping around a section of material connected to the most famous ship in history, keeping it in a condition that the wreck itself could never maintain at the bottom of the Atlantic Ocean. Scientists who study the Titanic wreck site know something disturbing. The ship is disappearing. Microbes are consuming the steel. The entire wreck could be structurally gone within decades. The ocean is winning. But this buried section, protected, sealed, time-locked, and what researchers believe it could tell us about how the Titanic was actually built, the real engineering behind why it sank, is something the ship lying on the ocean floor can no longer answer. And by the end of this video, you'll never think about the Titanic the same way again. Let's start with what most people think they know about the Titanic. You probably know the basics. April 1912, struck an iceberg in the North Atlantic, sank in under 3 hours. Over 1,500 people died. The wreck was found in 1985 by Robert Ballard, lying in 2 pieces nearly 12,500 feet below the surface. Hundreds of artifacts have been recovered. James Cameron made the movie. You know this story. And the engineering explanation you've heard is simple. The Titanic hit the iceberg, the steel hull buckled, water flooded the watertight compartments. Too many compartments were breached. The ship couldn't float. Physics. Done. But here's the crack in that thinking. The wreck site itself, the physical evidence that could tell us exactly what happened and exactly how the ship was built, is deteriorating faster than scientists can study it. Microbial species discovered specifically on the wreck are consuming the iron at rates that alarm researchers. The crow's nest is gone. The officers' quarters have collapsed. Sections of the hull that could reveal vital engineering information are simply disappearing. That makes this buried discovery uniquely important. For the first time, researchers have access to preserved Titanic-connected material that has not been subjected to over a century of deep ocean chemical warfare. Material in the condition it was in when it left the Harland and Wolff shipyard in Belfast in 1912. And what that material reveals about the construction of the Titanic and the hidden engineering decisions made in that shipyard is the story almost nobody is telling. So let's go deeper than anyone has ever taken you before. Let's talk about Harland and Wolff, the Belfast shipyard where the Titanic was built, because this is where the buried discovery actually matters most. The Titanic wasn't built somewhere separate from its legacy. It was built in Belfast. The land around that shipyard has been an active industrial site for over a century, and buried within that land, in the sediment and fill that accumulated over generations of industrial activity, researchers have now confirmed the presence of preserved material connected to the Titanic's construction era. Think about what that means physically. When ships were built at Harland and Wolff, the process wasn't clean. Steel shavings, rivets, material samples, construction waste, template pieces used to shape hull sections, all of this ended up in the ground around the facility, buried under layers of later construction, fill material, and industrial sediment, protected from the elements, protected from the ocean, protected from time in a way the ship itself never was. The specific buried material confirmed at nearly 60 feet depth includes construction-era steel samples and rivet specimens, the exact same type of riveting that has been at the center of a major engineering debate about why the Titanic sank so quickly. And here's where the engineering gets genuinely important. For decades after the wreck was found, the standard explanation was simple: iceberg impact, hull breach, flooding. But metallurgical scientists who have studied recovered Titanic artifacts have found something that changes the picture dramatically: the rivets. The Titanic's hull was held together by approximately 3 million rivets. The steel hull plates of a ship that size don't fuse together. They're connected by these rivets, driven through overlapping plates to create watertight seams. And the quality of those rivets matters enormously to how the hull behaves under sudden violent stress. Analysis of rivets recovered from the Titanic wreck site showed that the iron rivets used in certain sections of the hull, particularly in the bow and stern, where the iceberg struck, contained significantly higher levels of slag than engineering standards of the time recommended. Slag is a glassy waste material that forms during iron smelting. In small quantities, it's acceptable. In high concentrations, it makes metal brittle, prone to fracturing suddenly under impact rather than bending and absorbing force. But here's the part that nobody talks about. The debate about whether those recovered rivets were truly representative of the ship's construction or whether ocean exposure had altered their composition over a century has never been fully resolved. Deep ocean chemistry is aggressive. It changes materials. Any rivet pulled from 12,500 feet of salt water after 112 years carries the chemical signature of its time in the ocean mixed with its original composition. The buried Belfast material carries no such contamination. It is, in metallurgical terms, a control sample, the same era, the same shipyard, the same construction period, but untouched by the ocean. That is why researchers are calling this one of the most significant Titanic-related discoveries in decades. Wait, it gets even more interesting. The wreck of the Titanic has never been fully accessible for detailed scientific study. You can send remotely operated vehicles to photograph it, you can retrieve artifacts from the debris field, but you cannot safely access the interior structure in detail. You cannot take systematic material samples from the hull. You cannot run comprehensive metallurgical analysis on the steel at the point of impact. The ship is too fragile, too deep, too deteriorated. What that means for understanding the Titanic's engineering is that researchers have always worked with incomplete evidence. They've worked backward from the visible damage. They've modeled the flooding sequence using computer simulations. They've extrapolated from a small number of recovered artifacts. The 1997 academic paper that first raised serious questions about the rivet quality, published by scientists Jennifer Hooper, McCarty, and Timothy Foecke, was groundbreaking precisely because it provided physical evidence that the ship's construction might have been compromised by material quality issues. But the sample size was limited. The ocean exposure variable was always present. The buried Belfast discovery changes the research equation in a fundamental way. For the first time, the metallurgical question, were the Titanic's rivets compromised by high slag content as a construction-era decision or as an artifact of deep ocean chemical exposure, can now potentially be tested with a clean dataset. Here is the most shocking fact in this entire video. The answer to one of the most debated questions in maritime engineering history, why the Titanic sank in less than 3 hours when it should have survived much longer, may have been sitting 60 feet underground in Belfast this entire time. Not in the ocean, not in the wreck, in the soil of the shipyard where the ship was born. You've probably heard stories about engineering disasters that came down to a single material decision, a wrong specification, a cost-cutting substitution, a compromise in quality that seemed minor at the time. The O-rings on the Space Shuttle Challenger, the de Havilland Comet aircraft whose square windows created stress concentration points that caused catastrophic mid-air failures. The Tacoma Narrows Bridge whose engineers hadn't fully accounted for aerodynamic resonance. In every one of those cases, the disaster revealed a hidden engineering vulnerability that was invisible during normal operation and only became catastrophic under specific extreme conditions. The Titanic rivet question follows exactly the same pattern. During construction, during sea trials, during the early voyage, the rivets performed normally. It was only under the sudden, violent, asymmetric stress of an iceberg impact that the high-slag iron rivets in the bow section potentially failed catastrophically, popping rather than bending, opening seams rather than holding them, allowing the flooding sequence to progress faster than the ship's design could handle. The same principle, material behavior under normal conditions being completely different from material behavior under sudden extreme stress, applies to modern engineering in ways most people never think about. Cold temperature steel specifications in Arctic oil pipeline construction exist specifically because of this lesson. The steel used in pipelines crossing Alaska and northern Canada is certified for low temperature ductility, because steel that performs perfectly at room temperature can become catastrophically brittle at -40 degrees Celsius. Engineers learned this lesson in part from analyzing disasters like the Titanic. The next time you hear about engineers specifying materials for extreme conditions, for cold environments, high pressure, sudden impact, know that those specifications trace their intellectual history directly back to disasters like the Titanic and the engineering investigations that followed. And this buried Belfast discovery could finally close the loop on the most debated element of that history. Now here's something that most people never connect to this topic. The Titanic wreck is not simply deteriorating randomly. Scientists studying the biological ecosystem around the wreck have discovered that a specific species of bacteria, Halomonas Titanicae, named after the ship itself, is the primary agent consuming the iron hull. It was discovered on the wreck in 2010 by a Canadian-Spanish research team, and it's extraordinarily efficient. The rustical formations hanging from every iron surface of the wreck, those orange stalactite-like structures that make the wreck look almost alive, are the physical output of Halomonas Titanicae consuming the iron and leaving behind iron oxide as waste. Think of the buried Belfast material like a sealed time capsule sitting inside a vault, while outside the vault someone has been slowly eating the original copy for over a century. The vault held, the outside copy is almost gone. What's inside that sealed vault, the buried construction-era material, may be the last clean window researchers ever have into the true material composition of the ship that the world spent more than a century trying to understand. The ocean will eventually consume the wreck entirely, but the soil of Belfast will hold its secrets for centuries more. So here's what we uncovered today. Scientists have confirmed preserved Titanic construction-era material buried nearly 60 feet underground in Belfast, untouched by ocean chemistry, intact in a way the wreck itself can no longer be, giving researchers for the first time a potential clean baseline for the metallurgical debate about whether compromised rivet quality contributed to the Titanic sinking faster than it should have. The rivet quality question, first raised seriously by academic research in the late 1990s, has always been complicated by the uncertainty of ocean exposure on recovered samples. The buried material removes that variable entirely. And while Halomonas Titanicae slowly consumes the last physical evidence at the ocean floor, the answer to one of maritime engineering's great unanswered questions may have been in the Belfast soil this entire time. The most important part of the Titanic was never at the bottom of the ocean, it was in the ground where the ship was born. Now I want to know, did you know the Titanic wreck was actively being consumed by bacteria? And do you think the rivet quality was the real reason it sank so fast? Drop it in the comments right now. I read every single one. In our next video, we're going somewhere that makes even this discovery look simple. We're going to find out why the most advanced passenger aircraft ever built had a fundamental engineering flaw in its fuselage design, and why engineers knew about it, and why the planes flew anyway. And what happened when the physics finally caught up? The world is not what it looks like on the surface. It never was. This is Logivra, and the logic was always there. You just needed someone to show you where to look.